Welcome to my new calculus channel. I am John Gabriel. In this video I'm going to talk about the derivation of number, in particular the Euclidean derivation of number, which is the only valid derivation. It may sound a little bit arrogant for me to say the following, but I'll say it anyway because it happens to be a fact. After Euclid and before me, no one understood what is a magnitude or what is a number, and no one even came close to understanding what Euclid was trying to accomplish in his book with respect to the derivation of number. So I'm going to show you now how to derive numbers from nothing, and obviously it has nothing to do with set theory, because there is a set theory derivation which is entirely wrong and very flawed in almost every aspect. But I'm going to focus in this video on the Euclidean derivation. So let's look at qualitative measurement. Well, what is qualitative measurement? It's measurement without numbers. So the first thing that we notice about qualitative measurement is that we can't really say anything about magnitudes. Before we continue, let's quickly define magnitudes. What is a magnitude? Let's go to the original definition in Greek. A magnitude is a part of another magnitude. This is not a very good definition, and the reason for that is it's circular or self-referential. The Greek says meros esti megathos to elason tu mizonos otan katametri to mizon, and basically it's saying that really a magnitude is just the idea of size, extent, or dimension. So that's the original definition of magnitude. It's not a number, by the way. A magnitude is decidedly not a number of any kind. Okay? So let's get back to our slide here. I said that qualitative measurement is the measurement that's done by just looking at magnitudes and deciding which magnitude is greater or smaller, and one can only do this visually without numbers. So for example, if you look down here at the red and the blue line, if we can tell that they're different, okay, so let's just make them the same, 3. So in this case we can't tell that they're different, in which case we can't say anything about the lines, right? We can't say anything about the lines in this case. But if we can tell they're different, like so, then we know which line is longer and which line is shorter. So what we do now is we acknowledge that qualitative measurement deals only with magnitudes, no numbers are involved, and we can also call this qualitative trichotomy. A very important fact to realize from all this is that measure came before number. Yes, measure came long before number. The next part of this derivation is, what is a ratio? And again, a ratio is a magnitude. Well, first of all, a magnitude is the idea of size, dimension, or extent, what I just showed you now. And a ratio is simply a comparison of any two magnitudes. That's literally what a ratio is. It's saying, okay, look at these red and blue lines here. We compare the two, and that's what a ratio does. So if we had to write AB colon CD, as you see here, read as AB compared with CD, that's called a ratio. So if you look at Euclid Book 5 and Definition 3, let's go back to Book 5 and Definition 3. A ratio is a certain type of condition with respect to the size of the two magnitudes of the same kind. Okay, so that's all it really is. It's literally a comparison, and the first ratios were comparisons of magnitudes, not numbers. So using ratios of magnitudes, we can only carry out qualitative measure. Okay, and that's obvious, right? Okay, so the next step is to establish a standard of measurement. In order to do this, one needs a magnitude that can be used to measure other magnitudes. So given two magnitudes A, B, and C, D that are commensurable, commensurable means they have a common measure or common magnitude that measures both. The unit can be any of the following three. A can be the common magnitude in this case, which is 4, the green line. It can be the magnitude AB, which is the blue, the magnitude AB here, which is the red line, or CD, which is the blue line segment. So we can choose any one of these to be the unit. 4 because it measures both 20 and 32. In other words, it's a factor of 20 and 32. 20 because we can measure 32 in terms of 20, and 32 because we can measure 20 in terms of 32. So if we move any of these along, we can see what happens, right? So if you have 20 and 40, the measurement is 20. Don't look at the length of this green line and say, well, it's longer. It's just, you know, it's not really longer than these. I'm just using it to illustrate that it's a common factor of both these numbers, the red and the blue. Not numbers, both these magnitudes. So once the unit is established, either magnitude can be described in terms of the unit. Yes? And that definition comes in Euclid Book 7. A unit is that according to which each existing thing is said to be one. Well, that was the definition we just made. And now the number, as we're looking at in here, once a unit is established, the number is just a multitude of units. We're getting to that in the next slide, but so far we're just looking at the unit. And each magnitude can be described in terms of the unit. So now that that's in place, we can now perform not qualitative measurement, but quantitative measurement. Okay, so how does that work? Well, quantitative measurement occurs when two numbers are compared. So it's also a ratio. Quantitative measurement is also a ratio, but it's a comparison of numbers. So if you have PQ or QP, then you're looking at a ratio of numbers, because numbers are multiples of units. And if you have a ratio in which the first part, which is called the antecedent, is smaller than the second part, which is called the consequent, or the numerator or denominator in modern terminology, then what you have really is a way of specifying numbers that are whole or mixed numbers, and also numbers that are just fractions. So if P is greater than Q, then you have an improper fraction, and if Q is less than P, you have a proper fraction. And by moving the sliders and the points on these lines here, you can see how that works. Yes, so for example, now if you increase this particular slider, you'll see the relationship of the different numbers. Okay, and all we can tell at this point now is that they have a difference. So for example, if you have 15 and 6, the difference is 9. Yes, 15 and 6, the difference is 9. And so we can now perform quantitative measurement. The next step is the derivation of fraction. So a fraction is just a ratio of two numbers. Actually, all numbers are fractions. Even the natural numbers are fractions. They're just fractions in which the antecedent is a number and the consequent is always a unit. So in this example here, we have P over Q is equal to 12 over 6. And we read that as 12 parts of 6 equal parts, where 6 equal parts are 1 unit. So I just want to pause here for a second and show you something. If we look at the theory of fractions, and here we are looking at paintbrush here. So if you have any fraction P over Q, what you are essentially doing is saying that the unit has been divided into q equal parts. Q equal parts, yes. And this antecedent tells us how many of those equal parts we're talking about. So let's look at an actual example. If you have 3/5, that means you've divided the unit into 5 equal parts, right? 1, 2, 3, 4, 5. And you can just choose any 3 of them you like. Okay? And these shaded parts are the number that we're considering. So 5 tells us that we have 5 equal parts, and we're only interested in 3 of those parts, and that's what a fraction tells us. And in this case here, 3/5 doesn't mean 3 divided by 5. There's no division taking place. The division has already taken place. All we're doing is enumerating how many parts of those that we want. That's why this is called a numerator. And 5 is called the denominator because the unit has been divided into 5 equal parts. Okay? This little horizontal line here is called a vinculum. And now there is a situation where the vinculum does mean the same thing as division, or the obelisk sign. And the situation in which it does mean the same thing is if P is greater than Q. Whoops, let's go back to if P is greater than Q. So for example, if you've got 7/5, then that means 7 divided by 5, which is equal to 1 plus 2/5. See, there's no more division taking place here. The division has already taken place, right? 2 is not being divided by 5. It simply just means 2 parts of 5, any 2 parts of 5. Yes? Oops. There we go. Okay, so this is an interesting part, fractions, that most professors don't even think about or have never heard about or learned about. They don't really understand fractions. And set theory doesn't do much to help, because set theory really confuses things when it comes to fractions. It defines rational numbers as pairs of integers. So for example, mn or m or nm are 2 rational numbers, okay, where that's mn and that's nm, or m over n, or n over m. This is in set theory, okay, and it doesn't really tell you very much about a fraction at all, but this here helps you to understand exactly what is a fraction. So very well, let's go back to the diagram here and see now that once we have qualitative and quantitative measurement in place, we can form the fractions. And this, by the way, is what is known as a derivation of number up to rational numbers, because fractions are rational numbers. There are no other numbers. Okay, there are no numbers past the rational numbers. Yes, I know you will hear the expression irrational number, but there is no such thing as an irrational number. There is, however, such a thing as an incommensurable magnitude. So what are incommensurable magnitudes? Magnitudes, now remember, are not numbers. Okay, as I showed you right at the beginning of this presentation, magnitudes are not numbers. Incommensurable magnitudes have no common measure with any other magnitude. So that means if you have 2 line segments whose distance is the magnitude, there is no magnitude that can measure both of them, and neither measures the other. A very common example is square root 2. So square root 2 cannot be measured by the unit. If any magnitude cannot be measured by the unit or parts of the unit, it's not a number. It's an incommensurable magnitude. Let's take a look at how we can approximate square root 2. Well, here's a right angle triangle with isosceles legs here, and in this, to begin with, I'm going to say that each of these legs has been divided into 10 equal parts, right? In other words, 1 here corresponds to 10, 2 corresponds to 100 equal parts, okay, 100 equal parts here, 3, 1,000, and so on. So if we have 10 which corresponds to the unit 1, then we can say, okay, well, in this particular case, when we try to measure the hypotenuse, which happens to be the magnitude square root 2, then we have 1 unit, and whatever remains here is incommensurable. Only part of it can be measured, okay? And so we can see if this is divided into 10 equal parts, then this here has at least 4 equal parts in it, but a little extra. So we can get to have some more precision if we divide the legs into 100 equal units. And so we do that, and now we see, well, we can still have 1.4, right? 1.4, yes, because now we have 41, at least 41 equal units in here. And so as we move that along, we can get to measure this magnitude better. In each case, we can increase this precision, but there is always a part, this part here, that is incommensurable. Okay, this part here contains I'm sorry, a magnitude that can never be measured. You can also look at the quick derivation of numbers in this little slide here, and just dismiss it after you finish. This is a derivation of number in 5 steps. Okay, and so let's get back to the previous slide where we were looking at incommensurable magnitudes. Square root 2 is not an irrational number, it's an incommensurable magnitude, and there are many of those. There's pi, there's e, and many others. And so here's a more sophisticated way of calculating square root 2, but as you can see, that can also give you varying precision depending on what the value of z is, right? So if we move z along, we can get a better expression for square root 2, right? That infinity symbol is not actually attainable, so square root 2 is never really equal to that. It's always approximated by this, so this equal sign here should really be understood to be an approximation, not an equality. And in this slide here, we can derive arithmetic axioms from the Euclidean derivation. So for example, if you wanted to reify the integer number line in quantitative measurement, from this we define the difference axiom, which is the difference in p and q is the distance between p and q, and we can denote the negative integers as minus p or minus q respectively. And the sum of two integers is defined in terms of the same difference, right? So the sum is defined in terms of the difference. And we can proceed to define division and also multiplication and everything else from the most primitive operator, the difference operator. And the last slide just gives you more information. So that's pretty much it for the derivation of numbers. I will put links to these two applets so that you can experiment or play around with them on the website, and that is the end of the presentation on the Euclidean derivation of number. This is John Gabriel. You're watching the New Calculus channel. Thanks for joining.